Process analysis is necessary in nearly all industries to meet safety and environmental regulations, increase productivity, conserve energy, and help ensure final product quality. Process analyzers monitor a process stream by sampling and measuring the components found in a stream sample. Analyzers provide both quantitative and qualitative information. Quantitative process measurement provides information on how much of each component is in the sample. Qualitative process information indicates the chemical composition of the process materials. Qualitative analysis can also indicate the amount of each sample component. Three important applications of process analysis are quality control, safety, and environmental monitoring. Analyzers help ensure that intermediate and final products meet specifications. Information provided by analyzers is used in the process control system to help stabilize industrial processes, thus preventing dangerous accidents. Analyzers can also provide early warning of hazardous situations so that corrective measures can be taken. Government regulations require process and emissions analysis. Analyzers are an effective means of monitoring the environment inside and outside industrial facilities. Two methods of process analysis are continuous analysis and automatic batch analysis. Continuous analyzers provide uninterrupted process monitoring. Automatic batch analysis measures process materials by taking discrete samples on a periodic basis. In the next segment, you'll learn about one type of batch analyzer, the gas chromatograph. Gas chromatography is a method of analyzing complex samples based on the physical separation of sample components. The gas chromatograph is widely used in process control because of its ability to separate complex materials, its high sensitivity, and small sample size requirements. Let's use this simplified drawing to see how a gas chromatograph operates. In a gas chromatograph system, the sample is continuously flowing from the sample conditioning system through the sample injection valve. The carrier gas flows into the sample injection valve and through the gas chromatograph. During sample injection, the carrier gas sweeps a pre-measured amount of sample through the column where separation takes place. The detector reacts to each of the components as they exit the column. Based on the reaction, the electrical section measures and records the type and quantity of each component in the sample stream. The sample injection valve, column, and detector are housed in the oven. Control systems maintain a constant temperature for system stability and to help produce accurate and reproducible analysis. The programmer controls the operations of the analyzer. This includes sample injection, column switching, detector signal conditioning, oven temperature, and data transfer. Gas chromatographs generate a readout called a chromatogram. The technician uses chromatogram data to configure the programmer for specific operations. The vertical axis displays peak height and represents the signal generated by the detector system. Greater component concentrations generate stronger signals. The horizontal axis is the chromatogram baseline, representing zero concentration. The horizontal axis length under each peak is the peak width, and the length between each peak is a measure of peak separation. Retention time is the interval between sample injection and the point of maximum detector response. On this example, the retention time is 5 minutes. Components that interact strongly with the column packing elute slower and have longer retention times. By looking at a chromatogram, technicians can determine column efficiency for specific applications. The concept of theoretical plates helps express column efficiency. To understand this concept, consider a distillation column. The more trays, the better the distillation. Although a chromatographic column does not have trays or physical plates, its number of theoretical plates is a measure of its efficiency of separation. Column efficiency is a function of HETP, or height equivalent theoretical plates. HETP is the actual column length, or L, divided by N, or the number of theoretical plates, which is a calculated value. Larger values for N decrease HETP. Shorter column length reduces analysis time and produces narrower chromatogram peaks. Resolution refers to peak width and the distance between peaks. In general, shorter column length and more theoretical plates improve chromatogram resolution. Resolution reflects column efficiency. Oven temperature, sample size, carrier gas flow, and carrier gas type also affect column operation. Because the effects of these items alone can look similar, experience and knowledge of your system can assist you in correcting problems with chromatogram resolution. Oven temperature can directly affect the analysis. Excessive heat affects separation, resulting in peak interference, which is the overlapping of peaks. However, excessively low temperatures can cool the sample below its vaporization point. Notice the effect on both column peak and width for this sample where oven temperature is too high. When oven temperature is lowered, this is the resulting chromatogram for the same sample. Sample size can affect separation and sensitivity of the detector. Sensitivity is the ability of the detector to measure the concentration of a component with respect to the sample size. For example, detectors may not be able to measure low concentrations of components in small sample sizes. Sample sizes that are too large may reduce separation, which may cause peak interference. The flow of carrier gas must be sufficient to transport the sample through the columns and to flush or purge the columns to remove old samples and any undesirable components. Flow rate is dependent on the specific application. Higher pressures may be required for flow through longer columns. However, excessive pressure and flow rates may reduce separation. Lower flow rates may lengthen analysis and elution times. If tests indicate insufficient carrier gas flow, pressure can be adjusted to meet the requirements of your particular application. Carrier gases must not combine chemically with the sample or with the column packing, or damage the detector. They should be pure to avoid false readings. Carrier gas selection depends on specific applications. Helium is a common carrier gas. Others are argon, nitrogen, and hydrogen. In the next segment, you'll learn about sampling system maintenance. But for now, review your workbook to learn more about gas chromatograph operation. An analyzer sample system continuously selects a representative process sample and rapidly transports the sample to the analyzer. The sample's flow rate, temperature, and pressure are conditioned to be used by the analyzer. Most sample conditioning systems require filtration to remove undesired particles from the sample. Filter type depends on process properties and on the type of analysis. There are two basic filter types: filters that are designed to trap occasional particles and filters that are designed to continuously filter all particles out of the process flow. Filters that trap only occasional particles should not be used in a system that requires heavy filtration unless the necessary maintenance time is available. Filters designed for continuous use may be self-cleaning. Once the sample has been conditioned and analyzed, the unused sample portion is discharged as waste or returned to the process stream. Process sample selection and transportation must be timely so that the sample will accurately represent the current process conditions. Most problems with analytical systems occur within the sample system. Proper sample system maintenance ensures optimal performance and analyzer data integrity. The approach you take to your work will depend on the maintenance task at hand and the process properties. Always consider safety when maintaining any analyzer system. A process may be flammable or toxic, and you might come into direct contact with the process sample. Determine process components and required safety and protective equipment before beginning any maintenance. Follow your facility's guidelines and maintenance instructions for any specific safety information. Once a problem has been verified, alert control personnel to the time and location of your work. First, check the flow meters to make sure the sample is flowing from the tap through the sampling system. If the flow appears to be normal, the problem may be in the analyzer and not in the sampling system. If there is low or no flow, there may be a leak or blockage within the sampling system. If you suspect a leak, use a leak detector to determine its location. If no leak is found, check for blockage. Since all filters eventually block, most manufacturers recommend routine filter replacement. When selecting a filter for replacement, be certain to use the correct filter for the process and for the type of analysis. If blockages are causing too much downtime, it might be necessary to reevaluate your filter maintenance schedule. To replace the filter, block and depressurize the system. In this example, it's necessary to remove the filter housing and filter retaining nut. Then replace the filter element. Reinstall the filter housing and return the system to normal operating conditions. If conditions do not return to normal, the problem may be with the sample tap or probe. Your workbook has more details on how to correct these problems. Gas chromatograph analyzers require very consistent and specific pressure levels to provide accurate analysis. This sample conditioning system maintains and controls this pressure. Normally, the sample is driven by process pressure. Sample pumps can be used to drive the sample if process pressure is not suitable. However, their use is not recommended because they tend to detract from system reliability and need a lot of maintenance. If your system has a malfunctioning sample pump, identify the pump by manufacturer and model and consult the appropriate manuals for repair or replacement guidelines. Check pressure gauges for proper operation. If a gauge is not operating properly, clean or replace as required. Steam or electric heat trace lines may also be utilized in the sample system. Make certain each end of the line is connected according to specifications. A multi-stream switching system like this one has multiple valves, filters, and flow rate indicators. Routinely check knockout pot valves to be sure they are open and the lines are unclogged. Any knockout pots or steam traps may have to be cleaned to keep accumulation from disrupting the sample stream flow. To check a filter on this gas chromatograph multi-stream sample system, disconnect the line from the filter to the bypass rotometer. Disconnect the sample in line and remove the coalescing filter. Open the filter housing to check the filter element for debris. If it's dirty, replace it. This filter element is free of debris and can be reinstalled. Flow rate indicators should also be checked. If the flow rate is too high or low, or if it drifts more than anticipated, the indicator may be clogged. Also, check for condensation in vapor samples and check for bubbles in liquid processes. Condensation or bubbles can adversely affect flow indication. Clean or replace the flow rate indicator according to manufacturer's instructions. A multi-stream system directs sample flow from several process points through one analyzer. Each sample stream is conditioned according to its own specifications before entering the analyzer. It is critical that the multi-stream sample handling system prevents the process streams from mixing or becoming contaminated. To prevent sample contamination, a double block and bleed design is often used with multi-stream systems. Parallel valves are used for each sample stream. The tubing between the two valves is vented, and a secondary bypass is used to clear all the sample lines. As you can see, the samples not being analyzed are diverted through the bypass rotometers and are either returned to the process or vented to flare. The continuous flow ensures a current sample is always available for the analyzer. Meanwhile, both valves are open on the sample stream that is flowing to the analyzer. The most important maintenance consideration for a block and bleed arrangement is to prevent contamination. Contamination can result when the blocked valves diverting flow of unwanted streams leak into the analysis stream, invalidating the sample. Contamination is a common cause of failure for both electric and pneumatic stream switching valves. If the valves malfunction, clean and replace as necessary. Be aware that each sample system is unique, since each process requires specific forms of sample preparation. Consequently, the configuration and maintenance of the sample systems may vary. In the next segment, we'll be looking at gas chromatograph valve maintenance. Your workbook contains additional information on sample handling maintenance. Sample injection valves inject a process sample into the column. For the analyzer to operate most efficiently, the sample injection valve must repeatedly deliver a precise sample volume. Sample injection valves can be externally heated or internally heated, depending on the requirements of the process. The three most common types of sample injection valves are sliding valves, rotary valves, and diaphragm valves. The sliding valve is designed to hold a small sample in a movable part of the valve known as the slider. Here's how it works. In the de-energized or rest position, process sample and carrier gas flow through separate loops of the valve. To inject the sample, a moving plate or slide takes a process sample from the sample loop and delivers it into the carrier gas flow, which sweeps it into the column. It's good maintenance to routinely inspect the slider valve housing plate and slider for corrosion. Damaged parts should be replaced. The rotary valve uses a sample transfer technique which is similar to the slider valve. In the de-energized or rest position, process sample and carrier gas flow through separate chambers of the rotary valve. However, to inject a sample, the valve rotates 60 degrees, redirecting the sample flow and allowing the carrier gas flow to sweep the process sample into the column. Check the rotating parts for cleanliness, abrasions, and corrosion. Damaged parts should be replaced. The diaphragm valve consists of 6 ports and 6 plungers, which are arranged in a circular pattern. Alternating sets of 3 pistons and plungers channel a sample from the sample loop into the carrier loop, where it is swept into the column. Under normal operating conditions, a sample injection valve may reliably perform 500,000 cycles. However, the operating life of a valve will be dramatically reduced if it's exposed to harsh treatment or contamination. Common valve problems include ruptured sealing discs, slow or erratic switching, valve leakage, and plugged valves. If your inspection indicates that the valve is plugged, it can be cleaned without disassembly. For this procedure, you'll need a large syringe fitted with a tubing adapter and filled with hexane, acetone, or methanol. You'll also need a small container half full of the fluid, a length of clear tubing, and a source of compressed air. Connect one end of the clear tubing to port 2 and place the end in the container of cleaning fluid. Begin by connecting the syringe to port 1 on the valve. Now, Use the syringe to force fluid through the passage between ports 1 and 2. Remove the tubing from port 2 and place it on port 6. Leave the other end of the tubing in the fluid. Switch the valve by applying air pressure. Use the syringe to force fluid between port 1 and port 6. Now remove the air pressure. Continue the procedure by attaching the syringe to port 3 and placing one end of the tubing on port 4 and the other end in the cleaning fluid. Use the syringe to force cleaning fluid through the passage between ports 3 and 4. Now, place the tubing from port 2 into the beaker. Switch the valve using air pressure. Force fluid between ports 3 and 2. Remove the air pressure. Attach the syringe to port 5 and place the tubing between port 6 and the container of fluid. Force fluid through the passage between ports 5 and 6. Now attach one end of the tubing to port 4 with the other end placed in the container of fluid. Use air pressure to switch the valve. Force fluid through the passage between ports 5 and 4. Reconnect the valve and verify proper operation. If you suspect valve maintenance problems, there are some troubleshooting procedures that can be done while the valve is in the analyzer. The chromatogram indicates valve leakage may be occurring. Since testing for leakage requires opening the analyzer oven and disconnecting the valve, you'll need to shut down the system. To do this, turn off the analyzer. Block the sample flow control valve. Block the carrier flow and allow the oven to cool. Valve leakage often occurs from the carrier port to the sample port, since the carrier pressure is often higher than sample pressure. Since this process is neither toxic nor corrosive, protective gloves are not required. Consult your facility guidelines for injection valve maintenance. To test for leakage, ensure carrier gas is connected to the carrier port. Cap the sample inlet and sample to column ports and attach a clear tube to the sample outlet port. Be sure that the pressure is maintained at normal operating pressure. Immerse the clear tube in a beaker of water. Bubbles indicate an internal leak. To repair the leak, it will be necessary to remove and disassemble the valve. First, disconnect remaining connections to the actuator. Then loosen the valve bracket screws. Slide the valve out of the bracket. Start valve disassembly by separating the cap from the body. In this example, relieve the pressure on the base screw and remove the 3 socket head screws. Remove the sealing and cushion discs. To remove the plungers, invert the valve body and shake it so that the plungers fall into the palm of your hand. If the plungers are stuck, wait until after the pistons are removed, then push them out from the bottom. Remove the manifold and the retaining ring. Next, remove the retainer base, compression plate, compression spring, and compensation plate from the bottom of the valve body. Use pliers to remove the pistons. Since the plungers were not removed before the pistons, push them out from the bottom. Clean and inspect the valve body pistons. Use a syringe to force cleaning fluid back and forth through each of the tubes of the valve cap while keeping the cap submerged in a cleaning solution. Rinse and shake out the tubes. Then let the cap air dry before reassembly. Wipe off grease and contamination from all other valve parts and wash them in the cleaning solution. Allow the parts to air dry. Install new O-rings and apply grease to the valve parts as the valve is reassembled. Apply manufacturer-recommended lubricant to the inside of the valve body. Place the assembly containing the spring, compression plate, set screw, base, and compensation plate into the valve body. Reinstall the retaining ring. When replacing the plungers, be sure to position them with the beveled end down. The top of the plunger is either dimpled like this one or flat. If any of the 6 plungers are installed incorrectly, the valve will not function properly. Tighten the base screw until 3 of the plungers protrude slightly further than the other 3. Place a drop of oil between each pair of plungers and use tweezers to move each plunger up and down to lubricate it. Leave any excess oil to be soaked up by the cushion disc. Loosen the base screw so the plungers no longer protrude. This will ensure that a plunger will not cut through a disc when the valve is reassembled. Install a new, dry O-ring on top of the valve body. It's good practice to replace the cushion and seal disc whenever the valve is disassembled. Position the cushion disc on the body over the plungers and place the seal disc over the cushion disc. Make certain the discs are aligned over the plungers. Align the valve body and cap and replace the cap screws. Adjust the base screw to give proper spring compression by turning it clockwise to a torque specified by the manufacturer. Reinstall the retaining ring and the manifold with 2 O-rings. Conduct a bench leak test. Once you have verified proper operation, the valve can be reinstalled. Replace the valve in the valve bracket. Tighten the bracket screws and reconnect the actuating air supply and valve ports. Turn on the carrier gas and actuating air and sample flow. Turn power on and manually operate the valve several times to seat the seal disc. Check for leaks with a liquid leak detector. More sophisticated analysis may require column switching systems that use multiple columns and column valves. One column provides a partial separation, while another column completes the separation for a detailed analysis. The use of additional columns can reduce the total analysis time and prevent column contamination. Column valves route the sample and carrier through alternate paths inside the chromatograph at different times in the analysis. Sliding plate valves and diaphragm valves are widely used for this purpose. Column valve design and maintenance is similar to sample injection valve design and maintenance. ISA's Instrument Technology Training Program is general in nature. When performing any instrumentation maintenance in your plant, be sure to follow the specific maintenance and safety procedures provided by your facility and the equipment manufacturer.